All right, so here we have a satellite of mass m orbits Earth at a speed of 5,921 meters per second. It says A, how high H is the satellite above Earth's surface, and then B wants to calculate the orbital period. All right, so let's crack it up. So in order to do this, let's set up your centripetal force, which is equal to the force of gravitational attraction. So here in the diagram, you have the satellite at 4 different locations here. And here you notice F of G is pointing direct towards the Earth. So we will say the Earth pulls on the satellite. At the same time, the satellite pulls on the Earth. But the Earth is going to cause the satellite to turn here with this F of G. All right. If we expand F of C, we have mv squared over x. Here, I like to use x because x is the distance from center to orbit. So it prevents a lot of errors from using the radius of the planet. All right. On the right side, f of g by definition is capital G times mass of the satellite times mass of the Earth, because these are the two masses for this particular problem, divided by x squared. F of g by definition is from center to center, so x in this case represents the distance from center to the Earth all the way to where the satellite is. So keep that in mind. So I just want to go ahead and point out x here is the distance from the center of the planet to the center of the satellite, or in this case, the satellite is in its orbit, so x and x here would be the same. All right, so keep that in mind. Here, I'm just going to go ahead and cancel out the mass of the satellite. So as you practice here, you notice that the mass of the satellite will be canceled because it doesn't matter in terms of finding orbital speed and stuff like that. All right, here I want to cancel x on the left side with the x on the right side. X squared would imply that you have x times x, because I have x times x, I can just cancel out that x squared. So that's just to simplify things. So on the left side, the only thing left is v squared. And then the only thing left on the right side in the numerator is capital G, mass of the planet, or in this case, mass of the stationary object, which in this case is planet Earth, and then divided by the distance from center to center. Okay. But here, it asks you to find how high H is, right? Or the height H that the satellite's above. So as you look at this, you notice here in my diagram, X includes from the center of the Earth to all the way to the satellite. So it actually includes H. So if you watch this, X to me in my diagram is the distance, the radius of the planet, add H, and that gives me X. So I can just solve for X. And once I solve for X, I can just do a quick subtraction, okay? So here I want to do a little switcheroo between x and v squared. I need to solve for x. So I'm going to bring x up to the top numerator. And then I want to bring the v squared down to the right denominator. And that's it. And here we have everything already. Capital G is the universal constant, which is 6.67 times 10 to the negative 11. The mass of the Earth is a constant of 5.98 times 10 to the 24th. You can look that up, or you can just, hopefully have it in your notes. And here, v squared, well, v is given in the diagram as 5,921. In addition, it's given in the statement there. And then don't forget to carry down your square, because this is v squared. If you punch all this in your calculator, you should get x is equal to 1.138 times 10 to the 7th. I just express my answer here in scientific notation, just so there's less values to type out. Okay. Well, you're not done here yet, right? You just found x, but part A asked you to find h. It didn't ask you to find x, it asked you to find h. So here in my work, I have a statement that's true. I said x is equal to the radius of the Earth plus h. So watch my cursor. If I start from the center and I go out to the surface of the Earth, that's the radius r. Well, I need to add this h in order to get to orbit. So x in this diagram is r plus h. Okay. Well, I know what r Earth is. So that's a constant. I know what x is. I just found that. So to find h, I'm just going to subtract both sides by re. So this re that's positive, I want to move to the left side of the equal sign. That makes it minus. So here, in order to find h, I simply take x minus r. Well, I know what x is. I know what r is. I'm just going to find h. So x I just found is 1.138 times 10 to the 7th meters, minus the radius of planet Earth, which is about 6.36 times 10 to the 6 meters. So if you punch all this in your calculator carefully, you should get a height of about 5.02 times 10 to the 6 meters. And that's your answer for part A. Okay, that's that. Now, for part B, it asks you to calculate the satellite's orbital period. So to calculate the satellite's orbital period, you need this particular function. Orbital period is here, right? you can use this function because speed is equal to distance divided by time. Well, in this case, we say the tangential speed is equal to distance divided by time. Well, the time here being the period because it's the time to complete one orbit. I do want to point out though here, this is 2 pi x. It's commonly written as 2 pi r because the circumference of a circle is 2 pi r. So the satellite is in circular orbit. Well, the orbit, the distance of this orbit would just be the circumference of this dashed line. Well, circumference in mathematics is 2 pi r. But here I have chosen to write 2 pi x because I think if you write r, you can troll yourself by using the radius of the planet, which is not the case. Because if you're looking at this diagram the way I'm looking at it, this orbit is a distance x away from the center of the Earth, not r. Okay, so here I'm just going to use x because it prevents a lot of misconception. So I made a note for you here. Well, I'm not sure where that arrow crosses x there, but it says do not use r Earth, right? So sometime out of habit, you might write 2 pi r because that's the circumference equation. But here I'm just going to write 2 pi x because x is the distance from center to orbit, which is the distance of this particular circumference. All right. Well, here I want to solve for t by switching it up. I want to move t up to the top left. I want to move v down to the bottom right. And then here, to solve for t, I need 2 pi x divided by v. Well, I already found x in the previous problem, so I'm just going to use it. Here, 2 pi I just carry down. X is the distance from center of the Earth to where the orbit is, or where the satellite is. And then x is calculated right here, where I'm circling. Okay. So x here is 1.138 times 10 to the 7th, which I just carry up here. Again, do not plug in the radius of the Earth here. Okay. Here, v is given to us as 5921. And if you plug this all in your calculator, you should get a value of 7.15 times 10 to the 7th in the numerator. And then the denominator is the same. And if you simplify that further on your calculator, you should get about 1.21 times 10 to the 4th second. All right. And that is that for part B. So the orbital period is 1.21 times 10 to the 4th second. Okay. I hope that helps. Stay nerdy. Don't be black.